So this is a summary of coursework that we do. So if you basically look at the electrical and electronics, we take automotive embedded systems, electric vehicle design. In mechanical, we look into autonomous vehicles. Some of the way that we develop coursework is we figure out the core technology areas where disruptions are happening, and we build coursework in that, and we help students take up that coursework and succeed in that course. Every coursework essentially has around 400 to 500 hours of learning, right? Usually our coursework are 8 to 12 months long. We have, as I said before, 250 plus coursework. And if you are enrolling in a coursework at Skill-Lync, you will be able to access some of the best industry experts who have recorded our coursework. You will have access to almost 150 to 200 hours of content. And also live tutoring. It is not only pre-recorded coursework. We do provide live tutoring with industry experienced professionals. And every coursework will be assessed, and as a assessment, almost 8 to 10 projects that you will essentially work on as a part of the course. Right? So it's a combination of pre-recorded videos with live support sessions and technical assessments. Here are some of the domain experts that we essentially work with in order to build some of the industry relevant courses. We believe that you can build industry relevant courses only when you work with industry relevant people. And therefore, all our courses are developed by people who work in the industry. So here's a summary of people. It's just an example of a snapshot that we essentially work with. So in this journey, we have also been fortunate enough to work with Bentley to partner and take their help in providing software access to students in order to make sure students have ability to install the software on their laptops and work on the assignments and projects that Skill-Lync provides as a part of the coursework. Our journey began in August 2020. Over this period, we have created 19 courses and almost 7 postgraduate programs using Bentley products. And we have done 40 plus webinars in the last 1 year alone using Bentley products. And the most important thing that we thank Bentley for is the licenses that they provide for not only for instructors to develop these coursework, but also for the students. Bentley has a great responsibility and the goal and the focus of providing knowledge to their student base, and that is being showcased by the number of licenses that they are willing and are also providing to students of Skill-Lync. Some of the tools that we cover as part of Bentley is STAAD Pro, Open Rail Designer, Open Bridge Designer, Open Buildings Designer, MicroStation, Open Flows Water Gems, and Sewer Gems. Right? So these are, if you are someone in the civil engineering domain, and if you want to kind of build a core civil engineering portfolio and a career as you move forward in a career, this allows you to do that. Bentley allows you to do that, and our partnership with Bentley essentially enables you to take up our coursework and use the software to understand in depth of the subjects that you're studying. I'm glad to introduce the speakers today, Mr. Sudip Narayan, Manager of R&D at Bentley Systems. We are fortunate enough to have both of them to be a part of today's session, where they will explain how Bentley and its products are enabling a lot of infrastructure development across the world, and how it will be beneficial for engineers like you to take up Bentley-oriented training that will enable you to succeed in your careers. Thank you so much for this opportunity, and thank you so much for joining us in today's presentation. I'll kind of now take a backseat and let the presenters take this forward.
So I'll be starting off, and thanks Surya for the introduction, and thank you all for joining this session. Let me quickly share my screen. Thank you. So good evening, ladies and gentlemen. Thank you for attending this session. Thank you, Skill-Lync, for having me today here. And the topic of discussion today would be the dynamics of industrial structures with STAAD Pro CE. And the agenda for this session is to learn how we can utilize the various analytical capabilities that is available within the STAAD Pro environment, which can be utilized to do dynamic analysis of industrial structures. You might be knowing that that the dynamics of industrial structures is a specific requirement in the industries, and as a part of the course on the industrial structures, learning the dynamics of it would give you a lot of edge in the professional field. So the plan today is to discuss this in three categories. We will have a general discussion to start off with, and we will be covering most of this presentation on the seismic analysis of industrial structures. And finally, we will briefly speak on the vibrational analysis, or the forced vibration analysis due to equipments of the industrial structures. So that's the plan today. Just to give a quick background of myself, I had been a structural engineer, professional structural engineers for 24 years, and I had been in a pure technical support role for over 12 years, and then I had 8 years of experience in the user success team and the consultant route, which also included technical support. And yes, and I'm a out and out person with a deep technical bone within me. So that's about myself. Okay, so to start off the first phase of the discussion, we will talk generally about dynamic analysis. It doesn't necessarily apply only to industrial structure. It would apply generally to all the dynamic analysis of the structures. So of course we can start off with the equation of motion in the first thing, which is the backbone of the dynamic analysis of structures, and have taken this from as a screenshot from Clough and Penzian Dynamics of Structures book. So basically, when you have a time variant load applied on a structure, the structure resists it in three ways: as inertial load, as a viscous load, and a spring load, or a stiffness elastic load. And to solve this equation, what we actually STAAD Pro does is it employs something called a modal superposition method, where this differential equation is broken up or is being uncoupled into n separate differential equations. And to get the solution of those equations, we would need to solve the Eigen condition. So what appears on the screen is the Eigen condition. Now, STAAD Pro would employ numerical methods to solve this condition. Just a quick note on Eigen solution is there could be two possible solutions to this Eigen condition. As you can see, one is if the mode shape vector is 0. That's a trivial solution, because that would mean that the structure is not vibrating at all. The non-trivial solution is when you have this expression as 0, and that is what needs to be solved. So if you actually write that in the form of an algebraic expression, it would result in a polynomial equation of degree n, and thus you would be solving for the stiffness matrix and mass matrix are known to you. So what you would be solving for is the value of omega square, and you would get n values of omega as a solution of this. So that would be the n natural frequencies, and if you resubstitute back this the n values of natural frequencies into the Eigen condition, you will get n mode shape vectors. So that's what is being solved for before you even attempt to solve the dynamic equation. Now, this is a very demanding process, and we will discuss briefly as we go along about the Eigen solution methods that that is implemented in STAAD Pro. Now, one important thing to note here is to have a proper Eigen solution, you need to have a proper stiffness matrix and proper mass matrix. Now, stiffness matrix is sort of generated out of what you model as the structure, but the mass matrix needs to be needs a specific mass modeling. So we will talk about a couple of quick pointers on the mass modeling. So in STAAD Pro, masses are modeled as lumped loads. Just give me a second. Okay, are modeled as lumped masses using the various load items, and then the load values that you define in the load items, those are the force units, and you would divide them by acceleration of gravity, the value of g, to obtain the masses. And you know that the mass is a scalar quantity, right? It doesn't have any direction. But when you define a load, you would define the direction of the load as well. Now, those directions represents the possible direction of vibration of the masses. And to capture the proper dynamic effect, you should specify the direction of vibration of the masses in all the three directions. The mass needs to be absolute quantities, because this would actually rule out the possibility of erroneous eradication or cancellation of masses. And yeah, we have two ways of defining masses, the classical method and the reference load method. So let me quickly show you how we have done this as a classical method. So basically, we have this load case one, as you can see in this particular structure. And you would see that we have defined the loads as absolute values, and we have defined the loads in all the three directions, right? And but the question may be like, then how does STAAD know that these are masses and not loads? Those are distinctly two different things. Now, any load case that has any dynamic commands involved in it. So in this case, in this particular load case, we have time history commands, which are dynamic commands. So the other possible dynamic commands can be the response spectrum specifications, the modal calculation requested specification. All this would convey this information to STAAD that it's a dynamic load case. And what would happen is it would then treat the load items defined in that load case as masses and not loads, and it would divide the whatever load values that you have given here by the acceleration due to gravity to get the mass values. Now, there can be other way of defining the masses as well. Now, in this case, you can see that in the load case, we only have the time history commands, but we do not have the load items that would represent the masses. So what we have done, is we have defined a mass reference load case. Now, if you actually define the loading type as mass, it would mean that the STAAD would treat the items that you define in this reference load as mass items. So these are some general pointers as to how you should be defining the masses in STAAD Pro. And we have seen that users make a lot of mistakes when doing this mass modeling, which results in a complete different set of natural frequencies and mode shapes. Because we can see how important that parameter is for the Eigen solution, right? So now talking about the Eigen solution methods in STAAD Pro, we have the subspace iteration method. Now, you may be knowing that STAAD Pro has two modes. One is a normal STAAD Pro, which is the basic version of it, and a STAAD Pro Advanced. Now, both STAAD Pro and STAAD Pro Advanced has the subspace iteration method, which is a numerical method of solving the Eigen condition. And in the STAAD Pro Advanced specifically, you also have the Arnoldi-Langsos method of solving the Eigen condition. Now, both of these methods are extremely well-known numerical methods to solve the eigenvalue problem. But the advantage of Arnoldi-Langso's method is that in systems which are huge or which are substantially larger, you would have a faster convergence of solution using the Arnoldi-Langso's method than a subspace iteration method. But both of them are equally stable methods. I would like to talk about a specific type of eigen solution that we have, which is the load dependent Ritz vector, where we do not solve the eigenvalue problem using the natural modes, but we use we use the Ritz vector instead of the natural mode shape vectors. Okay, now let me show you a quick example of how this load dependent Ritz vector can help. Now, let me go to this particular STAAD model, and you can see that this is the model of a pipe rack structure, which is very long and which is a common case that you encounter in industries or the industrial structures. So in this case, if you actually go and I have already run the analysis of these structures to save time. And if you look at the participation factors of this, so let us say that you are doing a seismic analysis for this whole structure, okay, and you are doing a response spectrum analysis. Now, the code would require you to achieve a 90% mass participation in either directions, okay. Now, if we look into the participation factors here, you can see that there are, let me make the fonts a bit bigger so that you can see that easily. So you can see that, okay, we do have some good participation in the first 3 or maybe first 5 modes, but after that we do have a very insignificant mass participations, which a lot of it is due to the local flutter. And once you are satisfied that this is not due to any instability problems, you know that these are insignificant modes which doesn't help you get or obtain your mass participation, the total mass participation. So you can see that to get a total mass participation in the X direction of 90%, you need to run the whole system for at least 53 modes, but you do not have any mass participation in the Z direction. Now, and for getting the mass participation in the Z direction, you would need to run for even higher modes. And you would see that finally, in the 144th mode, you obtain the mass participation of 90%. Now, so it's a clear indication that there are a lot of insignificant modes in this structure. And if we do a natural, or if we use the natural mode shape solution to solve the eigen value problem, then, or the natural mode shape from the normal eigen solution that we have done, we would need to run for a lot of modes. Instead, if we use the Ritz vector, say, if I have gone to this and if I have used the Ritz vector, so if I actually go into, okay, one of the things that you could do is, okay, let me show it this way. So if you go into the text editor here, you can see that I have set the eigen method as Ritz. Okay, and if you actually run the Ritz vector, what will happen? You'd see that we actually obtain the participation in just 20 modes. And you can see that by 13th mode, we have run it only for 20 modes, and the first 13 modes gave a 90% participation in the X direction, and for the 20 for the mass participation, 90% mass participation in the Z direction, we had obtained it by the 18th mode. So it saves a lot of unnecessary time and a lot of unnecessary analysis time if we use Ritz vector instead of the natural mode shape vectors. In fact, a lot of the dynamic pundits around the world suggests using of Ritz vector than the natural mode shape vectors. So in STAAD Pro, you can use either of it. You can use um, um, for natural. If you want to use the natural mode shape vectors, you can use the Arnoldi-Langsos or subspace iteration method of eigenvalue solution. And if you have a lot of unnecessary insignificant modes, you can flush them out by using the Ritz vector. Okay, now let us go back to our slides. And this is the topic that we are going to spend our significant amount of our time on, which is the seismic analysis to IS 1893 part 4. And to start off this eigenvalue solution, sorry, I'm still in the eigenvalue solution mode, sorry for that. To understand the IS 1893 part 4, now I think I'm sure you know about the IS 1893 part 4. The part 1 is a well-known code, which is meant for solving or which are meant to guide you as for the seismic analysis for buildings or any other general structure. IS 1893 part 4 is specifically meant for industrial structures. There are two parts to that code. One is meant for general industrial structures, and the other section is specifically meant for stack-like structures. We are going to speak only on the general industrial structures for now. All right, so to understand the specifications of IS 1893 part 4 code, you would need to understand the definition of the various structure categories that code has defined. So category 1 structures. What is category 1 structures? Category 1 structures are those structures, the failure of which might result in extensive loss of life and property, not only within the plant complex, but also to areas adjacent to the plant complex. Category 2 structures would be whose failure might cause serious fire hazards and extensive damage within the plant complex. Category 3 structures would be those which the failure of which might be expensive but does not lead to serious hazards. And apart from all these three categories, all the other structures would be categorized as category number 4. Now, when we speak about the code, we will see how important it is to understand these particular categories. Okay, the code in clause 10 also gives us situations where we can choose to use dynamic analysis, or we have to use dynamic analysis, and there are situations where we can choose to use static analysis instead of dynamic analysis. So structures of category 1 in all seismic zones, you have to do a dynamic analysis. Structures of category 2 in seismic zones 3, 4, and 5, you have to do a dynamic analysis. Structures of category 3 in seismic zones 4 and 5 have to do a dynamic analysis. All the other structures can be analyzed using the simplified static analysis. We are not going to discuss the static seismic analysis in this course. The title is about the dynamic analysis, but I just wanted to let you know at this point that the simplified analysis is also has been implemented in STAAD Pro. Okay, and the dynamic analysis can be in two categories: time history analysis and response spectrum analysis. So this is what the code says. Now, there are a couple of additional mass modeling guidance that the code gives. This would be in addition to what I had just discussed, and what the code has suggested is to take or consider the structure equipment interaction properly. So industrial structures would generally have a lot of equipments that are stacked on it, or like it has cable trays, it has pipelines. So there are a lot of these equipments. There are machineries, vibrating machineries that sits on industrial structures. So So you have to consider the interaction between those equipments and the structure. So that's why there are some additional mass modeling guidelines given in the code. So if your structure has rigidly mounted equipments which are rigidly connected to the structure, you can model those as lumped masses. There could be flexibly mounted systems that is stacked on the structure. Flexibly mounted system would mean structures that are positioned on the or the equipments that are positioned on the structure using isolator supports, and you can still model them as lumped masses if the percentage of the flexible masses is less than 25%. But if the percentage of flexible masses is greater than 25%, the code suggests that the code envisages that this would lead to a structure equipment interaction, and you have to do a coupled analysis. So the code suggests to actually model the support system. Now, at this point, of course, we do not have the modeling of the isolator support systems in STAAD Pro, so we can only do an uncoupled analysis using the lumped masses at this point. So these are some additional guidelines that the code gives for seismic analysis of industrial structures. Now, what I have just discussed is only valid for category 2, 3, and 4 structures. Okay, it's a category 1 structure. It has a different requirement, which I am not discussing here. All right, the next thing is the design spectrum considerations. So if you are doing a response spectrum analysis, the code suggests that you would need to you need to develop the site-specific design spectra for all important structures. My suggestion would be, if your structure is in category 1 or category 2, you go for a site-specific design spectra. Okay. The code suggests that the horizontal seismic coefficient for the site-specific spectra is given by this equation, though if your SA by G values in this equation is not scaled to the peak ground acceleration, then you have to multiply that with the peak ground acceleration to scale it to that particular value. The code suggests that you have to compare that analysis with the standard design spectra that is given in Annex B of the code, which has to be taken as a minimum. For less important structures, you can directly use the code-specific response spectrum. And of course, it's given, the horizontal seismic coefficient is given by the well-known equation that is given here. Now, I just wanted to show you something. I had data on site-specific spectra, which was sent to me by somebody. It was steel structure, so I have only taken the 2% damping values here. And you can see that in this case, you can see against the 0 period, we have the SA by G value as 1, which is a clear indication that this has not been scaled to the peak ground acceleration. If the response spectrum is given, the data is given in this way, then the report would also have the recommendation for the peak ground acceleration to be considered. In our case, we can see that the peak ground acceleration is 0.24 G that was given by the report. Okay, so that would mean that your spectrum, which originally this is the elastic spectrum, the brown spectrum that you see, that's the normalized that's the unscaled elastic response spectrum curve. And when you scale that to the peak ground acceleration of 0.24 G, which would mean that you need to multiply. So this is the scale values. So you need to multiply the unscaled values with the peak ground acceleration to get the scale values here. And then the blue colored spectrum would give you the design-based values, right? The values that you would need to use for design. So, but you do not need to manually do this as I've done in this Excel sheet. All that you can do is you can define these values here, in STAAD Pro directly. So what I have done is I have taken these values in another sheet like this, and what I can do is I can copy these values and I can take it to think yeah, I'll add response spectrum load case here. So all that I do is I go and paste this value. So I have actually unscaled elastic response spectrum curve. I have defined the data here. Okay. And I can select the code, and you can see that we can select the IS1893 part 4 2015 code. And the combination method is I would always prefer CQC. The code suggests a few methods, but CQC, I've always preferred the CQC method because it takes care of any possible interaction between the closely shaped modes. So we take that as CQC. Oh, I think I had messed up something. Anyways, I need to choose the custom response spectrum and paste the values here. Let me check if I've done it correctly. Okay, yes. Now, you know that these are the unscaled response spectrum values. So we need to scale that down to the design-based values as I have just shown to you in the Excel sheet. So how can we do that? We can do that using the direction factor. So we need to define, let us say that we want to define the seismic load in the X direction. So what would be the direction factor? Let me quickly show you quickly the calculation of what the direction factor would be. So our direction factor, so we need to firstly, the unscaled values needs to be multiplied with the peak ground acceleration, which was 0.24g. So we multiply that with 0.24, and then those are still the elastic response spectrum scale to 0.24g. Now we need to bring that down to the design-based earthquake. So we multiply that. Our report had suggested that we need to multiply that with 0.5 to bring that to design-based values. So we multiply that with 0.5, and then we have to multiply that with the I/R ratio, which is the importance factor by the response reduction factor ratio. So let us consider that our structure is a category 2 structure, and let us say that it's in seismic zone 5. So in that case, if you look at table 3 of the code, the importance factor would be 1.5, and the response reduction factor, considering a steel frame with concentric bases, the response reduction factor would be 4. So the I/R value would be 1.5 by 4, that is 0.375. Now, if we substitute this value in the direction factor calculation, we get the direction factor as 0.045. So that's what we need to use as the direction factor. The time really is running out, so I have to do fast. Okay, and damping. Now we have to specify this as the damping value. Now a lot of users ask us this question, that we have already defined the spectrum for 2% damping. So why do we need to consider damping value again? Does this reduce the spectral acceleration defined even further? The answer is no. We would need this damping value to define the modal combination, because if you look at the expression of the CQC modal combinations, it has the damping factor in it. So this damping factor that we define here goes into the calculation of the CQC combinations. Okay, so we define the damping here. Now, next thing that we do is we need to define the scale factor. Now, in this case, we have the SA by G values. Okay, so we need to scale that up to multiply that by the value of G. So we have to multiply that with 9.81. And then the code requires, as per table 2, that you have a minimum lateral force requirement. There's a minimum lateral force requirement in table 2 of IS 1893 part 4 code. And for category 2 zone 5, it is 4.5% of the total seismic weight. So we select that value and we click on add. So this completes our spectrum definition. This is how you would need to define the spectrum specification to IS 1893 part 4 in STAAD Pro. Now, remember that the code also requires you to check it against the codes based design spectrum. So actually you need to have another load case. This is currently not automated. You need to have another load case with the code specified design spectrum. You have to check the base shares, and if uh, the design the code based design spectrum base share is higher, then you have to scale up the first results. So you have to just find out the ratio and take that ratio in that scaled in that scale factor, and then you delete the standard the load case related to the response spectrum that you have defined from the code. Okay, so that's the response spectrum. Quickly wanted to talk to you about the combining the component earthquake load cases. Now, the code says that if the plan-wise distribution of the mass and stiffness of the structural system is not symmetrical about the lateral axis, you need to consider a full component in one direction and 30% component in the other direction. So I'm neglecting the vertical effects here for now. So you have to, as a total earthquake case in one particular direction, you have to consider the full earthquake effect in that direction and the 30% effect of the earthquake in the other orthogonal direction. Now, or you can use the SRSS combination to find out the complete earthquake load before you take it to the design combination. All right. Now the question is, how do I know if if the mass and the stiffness distribution are symmetrical or not symmetrical? Well, I estimation works for simple structures, but for complicated structures, it won't be easy to make that out. But there are certain pointers in your analysis results itself. So I'll just wanted to show you that. So if you take this structure, for example, there's a clear difference, or there is a clear asymmetry of distribution of the mass and stiffness. So if you actually run the analysis, you just do a modal calculation requested command, and just go and check the modal participation factors, or the mass participation factors, and you can see that in the first mode, you can see that there is significant participation in both the X and Z directions. You can see if for the first mode you have a 24% participation in the X direction, 49% participation in the Z direction. For mode 2, you have a 55% participation in the X direction, whereas a 25% participation in the Z direction. And then you have a torsional mode. Okay, if you want to know whether it's a torsional mode or not, you have to actually verify that. It could be an insignificant mode, it could be a local flutter mode, but even torsional modes are characterized by these low values of mass participation. So to check whether it's a torsional mode or not, you have to go and check it in the post-processing mode. Now, how do I? Okay, just a second. All right, now if I go and wait a second, this one is able to, anyways. If I go to structure diagrams and pull this out, and if I go to where it was animation, if I go to modes, and if I go to apply, okay, now this is the first mode, and you can clearly see that there are some participation in both the X and Z direction. Now if I change it into mode shape number 3, this one, wait, if I change it into mode shape number 3, you can see that it's a clear torsional mode. Okay, so basically then mode shape number 3 is a torsional mode. So here's my suggestion, that if you do you can check your mass participation results, and you can, if you see that there are mass participation in the same mode in both the lateral direction, or if there is a torsional mode in the first 5 modes, you would know that there is definitely an asymmetry between the mass and stiffness distribution. Okay, and in those cases, you need to consider the 30% components as I have just shown. Okay. All right, now Now, this is something which is a bit advanced. It's called the floor response spectrum. I think I have 10 minutes, so I have to really go fast. So this is a frame, and you could see the mesh with the plates where we have a, just imagine that it's an equipment that is sitting over there. Okay. Now let us say that, so this is the area where the equipment is sitting. Now let us say that this structure is hit by an earthquake. Of course, you know that the earthquake motions will be affecting the base first, because it's the ground that would be moving. Now this would mean that the whole structure would start moving, right? And now the analyst of that equipment would want to know whether his equipment is safe against if this earthquake hits there. So how does he do that? Now he cannot use this direct earthquake signals that we have here because this acts on the ground level, right? But the equipment is sitting on the floor level. So he would need to know about the vibration at the floor level, which would be the base unit, base input for the equipment. Now, how we can do that is once this earthquake hits the ground, we do a time history analysis against this particular earthquake, and we get all the acceleration, the time dependent acceleration for that particular area where that equipment is sitting on, right? All the nodes. So we'll find out the average acceleration at all the time points in a particular direction in which we want to analyze the equipment. And then so we will solve this particular equation. Now, those acceleration that we have found out will be input on the right side of the equation as minus ft double dot. Okay, and then we would, what we'll do is we would then input the damping value of the equipment and also the natural frequency of the equipment and solve for the displacement. And from that displacement, we can calculate our spectrum or a response spectrum that can be used for earthquake analysis of that equipment that is sitting on the top there. So so this is the concept of the flow response spectrum. I just wanted to quickly show you how you can use that. So this is so I think, yeah, this is the flow response spectrum. So basically let me go to the analytical mode, and you can see that if I go into the loading option, what the first thing that we have done, so there is a dual time history solution that is done here. So we can see that in the first case, what we have done is we have defined a ground motion, and we have given the ground motion data as the EQ data here, which would mean that EQ data is nothing but we have a notepad file which actually has all the records of the El Centro earthquake. So we have input that motion at the base of the structure. We did a ground motion analysis, and then what we did was we actually defined this these values, and we said that we want to generate the spectrum for 2% and 5% damping, and we ran the analysis. The code actually, if we go into now in the post-processing mode, and if we go to the dynamics tab, or you do not even need to go to the dynamics tab, and if you go to dynamic and floor spectrum, you see that we have the floor spectrum. Now you can hand over this floor spectrum to the equipment analyst to give him an idea as to, so he can use this as an input for his equipment analysis. Okay, and you can change the values. So we have 2% damping, this and if we change it to 5% damping, the tables and the graph both would change. Okay, so and you can hand over this data to the equipment analyst, as I've said. All right, there is another way, another thing that you can do in STAAD Pro is that you can convert a response spectrum into a statistically equivalent time history load and actually analyze the structures for that. For example, as I'm running out of time, I won't show you the stat file corresponding to that. I have it. But now this can be important in cases of say category 1 structures. Now response spectrum doesn't capture the phase relationship between the various modes, okay? And this is only captured by the time history analysis, but you do not have a time history data for all possible cases. You only have the response spectrum data. So what the code now suggests, or the code around the world are suggesting, is that you can convert that response spectrum graph into a synthetic time history. Synthetic means artificial. That is, it is not an actual time history, but you convert that to a statistically equivalent time history and apply that as a ground motion to analyze the structure. Okay, so that we even have that facility in STAAD Pro. Now, that finishes the seismic analysis of industrial structures. We just wanted to spend a couple of minutes on the forced vibration analysis. So, I just wanted to tell you about a case that came to me once, where one of our users came to us and said that, their the structure that the structure that they have and the equipment that it is supporting, when the equipment runs, the structure vibrates so much that the cable is cut off or the pump is destroyed. A lot of things like that was happening because of excessive vibration. Now, what happens generally, what generally the engineers do is they actually only check the natural frequency against the forcing frequency to ensure that there is no resonance that happens. Um, but even if there is no resonance, if the stiffness requirement are not good enough, the structure will vibrate too much. And in this case, that was exactly what was happening. For that, you actually need to do a time history analysis, see the steady state results, and then convince yourself that the deflection that I'm going to get is not going to affect my equipments. So how do you do that? Okay, I'm just going to quickly show you, not this one, a steady state analysis case where you actually apply a time history load. Okay, and what you do is, let us take up, now this is a turbine foundation model that you see, and the time history loads from the turbine has been input as the forcing function on this turbine turbine model. And when we solve for that equation, what we see here, the way that we need to handle this is, you could see that there are some excessive displacements at the top now, at the beginning of the time, but then gradually it settles into a very steady pattern. Okay, so now the reason of why you see an uneven vibration at the beginning is because of the transient phase that is existent in the vibration. Transient phase is because of the natural modes of vibration that also takes place, but the transient modes of vibration, as you know, would die down because of the natural damping in the structure. And finally, once that the natural vibration dies down, all that would remain is the forced vibration by the equipment. So that's what you see. So what you need to do is you need to ensure that you run sufficient number of cycles so that you attain the steady state, and you would immediately get an idea of what the steady state is. Like, look at these areas, right? You could see that it has settled into a rhythmic vibration here. So this once this part was over, after this time, it settled into a rhythmic vibration. So this is the steady state that has been achieved. Now the engineer needs to check that whether this peak vibration, the peak steady state amplitude, is within tolerable limits. Will that keep the structure safe? That's what they need to do. Of course, it's important to check the resonating thing, but but even after checking that, it's very important to understand whether the steady state amplitude is within tolerable limits or not. There is another way of doing steady state analysis in STAAD Pro using the steady state module, and where we do a frequency domain analysis, and we run the analysis for a range of frequencies, and we have plotted all the frequencies against their peak displacements. Okay, and based on that, we can see like what machines would fit in the structure. And we have run it from around 3 hertz frequency to around 60 hertz frequency, and we can see that the highest response would be for a frequency of 6.231, where the displacement was around 0.125 millimeters. So this can be done by the steady state module, because once you are running or once you are interested in a force vibration results, you are generally interested in a steady state results. You are not interested really in the transient state. So you can use the steady state module to actually gauge a number of frequencies together using this particular graph. Okay, so steady state module again is available now. Most of the features that I have shown you, the advanced analysis features like floor spectrum, the synthetic time history, the steady state module, etc., they are available in the STAAD Pro advanced module. Okay.